So now we're going to be looking at a specific type of hypothesis test. Here we're going to be testing hypotheses regarding a population proportion. And so the material that we looked at in section 10.1 introduced you to the language of hypothesis testing. And in there we talked about the fact that there are three forms of the alternative hypothesis. There's a left-tailed, a right-tailed, or a two-tailed alternative hypothesis. In this section, we're going to be looking at hypothesis testing for a population proportion. So the null hypothesis is going to be that the population proportion equals some specific value. We're going to use P with a subscript 0. That's read P naught, like that, to represent the assumed value of the population proportion. And then you have three versions of the alternative. You have the two-tailed, in which case your alternative is a not equal to alternative. You have a left-tailed, and you have a right-tailed. In each of these hypothesis tests, the value of P naught is some proportion. It's going to be a value between 0 and 1. It's referred to as the status quo value of the population proportion. Another way to think about it is this is the proportion of no effect or no difference or no change from what we assume the value of the population proportion to equal. And then we go out and collect sample evidence to see whether or not the sample evidence in fact refutes our assumption about the value of the population proportion. To motivate this idea, I have a scenario for you. Suppose the proportion of registered voters who are registered Republicans in a certain congressional district is 0.42. In some states, the state legislature has the responsibility to redistrict congressional districts after the census, which is conducted every 10 years. After redistricting United States congressional districts in Illinois, members of the Republican National Committee wonder if the proportion of Republicans in the district is now less than 0.42. So in a random sample of 60 registered voters in that particular district, it's found that 22 are registered Republicans. Do the results of this survey suggest that redistricting resulted in a lower proportion of registered Republicans in this particular district? So first we want to determine the null and alternative hypotheses for this study. It's important for you to recognize the fact that the variable of interest here is whether the individual that was randomly selected is Republican or not. So this is a qualitative variable where there's two possible outcomes. Either you say, yes, I'm Republican, or you say, no, I'm not Republican. Because the variable of interest is qualitative with two possible outcomes, it makes sense to analyze this using proportions. The null hypothesis, remember, is always a statement of no change, no effect, no difference. So here, the statement of no change, no effect, no difference would be that the proportion of Republicans in the district after redistricting is the same as the proportion before, which would be what value? Equals what? 0.42. And we want to know if the proportion of registered voters who are Republican has gone down. And so we want to know if the proportion is what in the alternative? Less than 0.42. Okay. What's the sample proportion for the data that we collected from our 60 registered voters? In other words, what's the value of P hat? Yeah, 22 divided by 60, which if we work this out is 0.367. And so the question that we have to ask is the following. Is it possible to get a sample proportion of 0.367 from a population whose proportion is 0.42, or would we consider a sample proportion of 0.367 unlikely under the assumption the population proportion is 0.42? And when we say unlikely evidence, what we're really talking about is statistically significant evidence. And so what we want to do is figure out whether or not the observed results, namely 22 out of 60 registered Republicans, is unlikely under the assumption the statement in the null is true, under the assumption the population proportion is 0.42. If the results are in fact unlikely, then we have what's called statistically significant results, and we reject the statement in the null hypothesis. And so the question that we have to ask at this point is, how do we figure out whether we have statistically significant results? We're actually going to go about this a number of ways, in fact 2 ways. One is more traditional, where we actually use a model, and the other is using something called simulation. When we use the method of simulation, we're going to basically build something called the null model. We're going to assume the statement in the null is still true, and then what we're going to do is go out into the population and randomly select a bunch of individuals and ask them, are you a Republican or not? And then see how often we get results such as those we actually observed. Okay? So we're going to do this using StatCrunch. The idea here is we're basically going to build a population based on the assumption the statement in the null is true. So let's say there are 10 million registered voters in this particular district. If the statement in the null is true, then 42% of those 10 million registered voters should be Republican, with the remainder not being Republican, being something else. Democrats, Independents, Libertarians, whatever. And so take 42% of 10 million, that's 4.2 million, and we're going to put those 4.2 million into an urn. We'll just put them into an urn and call them balls. So make them green balls, right? And then we're going to take the rest, the 5.8 million red balls, and they're going to be non-Republicans, right? So we basically are building a population, a big vat with 10 million people in them. They're not going to be actual people, they're going to be balls. I'm going to go off to StatCrunch. I'll go ahead and open StatCrunch. And under Applets and Simulation, there's an urn. Click on the urn. We said the green balls we're going to have 4.2 million, 4,200,000. And then the red is going to be 5,800,000. We're going to draw 60 balls from the urn. What do the 60 balls represent? Yeah, the sample size, the 60 voters in the district. Ultimately, we're going to want to know how often we observe 22 or fewer that are Republican, because we actually observed 22 in our actual sample. We want to see how often we get something as extreme or more extreme than what we actually observed. If 22 out of 60 is extreme, certainly 21 or 20 or 19 would also be extreme, because that would be even a lower proportion that are Republican. Click Compute. What I'm going to do is click one run. And if you watch carefully what happens, I am basically selecting 60 balls out of the urn, asking each of those balls, are you Republican or not, and then recording the result. So when I click on this, each red ball, they're not Republican. Each green ball, yes, I'm Republican. And again, understand that that urn assumes the population proportion is 0.42. Now we're assuming that the urn was built assuming the population proportion is 0.42, because we had 4.2 million green balls and 5.8 million red balls. So in this particular time we went out and did the survey, we got 27 Republicans. I'm going to do it one more time. How many Republicans did I get? 30. So 30 out of my 60, or half, were Republican the second time I did it. You follow?
What constitutes the terminology of it being extreme? Like that extreme.
Okay, so we observed 22 out of 60 that were Republican when we actually conducted the survey, which was a sample proportion of 0.367. We wanted to know, ultimately, did the proportion of Republicans in the district go down, right? So 22 out of 60 constitutes the proportion going down, right? And then, so if that's unusual, certainly 21 out of 60 would also be unusual, right? So it's really because of the direction of the alternative hypothesis. So extreme is anything at the value that we observed or less, because it's a less than alternative. If we wanted to know did the proportion of Republicans go up, now we're talking about anything that way or higher, because it's a right-tailed or hypothesis. So in terms of what that run 1 represents is in a random sample of 60 registered voters, we had 27 indicating they were Republican. Right? Repeat part A, did you get the same results? Right? So if I open up run 2 here, you'll see that we did not get the same results. Why wouldn't we get the same results?
Sampling variability.
There you go. Excellent. Sampling variability. We surveyed different individuals, and therefore we're going to get different respondents saying, yeah, I'm Republican, and therefore you're going to get a different sample proportion. The results differ because we have different individuals in the sample. Now we're going to draw 60 balls at least 1,000 times. In other words, I'm essentially going to go out into this district, survey 60 people, ask them, are you Republican, over and over and over again. I said at least 1,000 times. I'm going to make it 5,000. So I have 5,003 times I went out there. See that? Out of the 5,003 times I went out there, how often did I see 22 or fewer that were Republican? 25% of the time. 1,230 times exactly. 1,230 out of 5,003 is 0.2459. It's super vital that you understand what we just did. We literally, first off, we have a population where 42% are Republicans, 58% are non-Republicans. We went out and surveyed 60 voters 5,003 different times. And each time counted how many are Republican. We observed 22 or fewer being Republican in 1,230 of the 5,003 times. So would you say it's unusual to get 22 or fewer Republicans from a population where the proportion of Republicans is 0.42? No, because it happened 25% of the time. This is exactly how you want to write it. We observed 22 or fewer Republicans out of 60 surveyed in 1,230 of 5,003 repetitions of this study. And this is all assuming the proportion of Republicans is how much? 0.42. Another way to think about this is the likelihood of observing a sample proportion of 0.367, that's the 22 out of 60, or less from a population whose proportion is 0.42 is 0.2459. In other words, you would obtain the types of results that you have obtained or more extreme in about 25 out of every 100 repetitions of this study. 0.2459 is about 25 out of 100. That number, 0.2459, is given a very special name in this class, in statistics in general. It's referred to as a p-value. It's the probability of observing a sample statistic as extreme or more extreme than the one you actually observed under the assumption the statement in the null hypothesis is true. Put another way, the p-value is the likelihood or probability that a sample will result in a statistic such as the one obtained if the null hypothesis is true, right? And that right there, 0.2459, is the likelihood of getting a 22 or fewer Republicans out of 60 if the population proportion is 0.42, if the statement in the null is true. And so would you say that the redistricting caused fewer Republicans to be in the district based on this result? Is this statistically significant? If you observe something that could happen about 25 times out of 100, if the population proportion is 0.42, would you say that that result is unusual? Not at all unusual. It could happen 25 times out of 100 by pure chance that you would only get 22 Republicans out of 60, even though the population proportion is 0.42. You saw it can happen that way. So the Republicans don't have a beef, at least from a statistical point of view. Click Options, Edit, and then under Proportions, I want to know the proportion that are less than or equal to 0.367 instead of less than or equal to 22. Watch what happens. So I got to click the run 1,000 times, a few times. And what do you notice the result here is? Practically the same. So whether you do the analysis on the counts of the number of balls or the proportion that is registered Republicans, you're going to get basically the same results. Describe the shape of the distribution of the sample proportions. What would you call the shape there? Pretty dang bell-shaped. See that? Pretty darn bell-shaped. I'm going to click Analyze. And when I click Analyze, something cool happens. In the data table, every single sample proportion that I just simulated pops into the data table. So in other words, in my, see how the first row says 0.467? Compute 28 out of 60 for me. That's 0.467. So the 0.467 in the data table is based on the fact that in my first time I did this, I got 28 that said I'm Republican. All right? If I click Run 2, I got 24 out of 60. Guess what that is? 0.4. See that in the data table for row 2? So in other words, this data represents the sample proportions that I got from each of the 5,000 simulations that I did. Again, going out and surveying 60 voters and saying, are you Republican or not? What I'm going to do is find the mean and standard deviation of these. Stat, summary stats, columns, the mean, and the standard deviation. So the mean of all of my sample proportions is how much? Essentially 0.42. What was the value of the proportion stated in the null? The standard deviation is what? 0.064. Is that right? Now we're going to do something really fancy schmancy. Do you remember how to find the mean and the standard deviation of the distribution of p hat? Essentially what you're seeing on the screen there, that little histogram, is a proxy for the sampling distribution of p hat, because that represents 5,000 different sample proportions. And if you recall from section 8.2, the mean of p hat should equal the population proportion. And our population proportion is 0.42, the proportion stated in the null. Remember, we assume the statement in the null is true, and so this data that's being distributed here, right, is based on the fact that the population proportion is 0.42. Remember, the formula for the standard deviation of p hat is the square root of p times 1 minus p over n. So 0.42 times 1 minus 0.42 over 60. Without even doing this calculation, I'm going to hazard a guess that it's going to be pretty close to 0.064. You see where the 0.064 is coming from? Let's see if I'm right. 0.42 times 0.58 divided by 60 is 0.0637, which is super close to what we got when we did this 5,000 times via simulation. This should be a mind-blowing experience for you. The mind-blowing experience is when you do the simulation, it matches up super close to what theory says should happen. In fact, in reality, you could stop with your simulation and don't have to do all the normal model business. You have an approximate value of the p-value of 0.25. You would not consider this evidence against the statement in the null hypothesis. However, the theory does match up to the simulation, so if you don't have access to a stat cruncher or something like that where you could simulate the results over and over and over again, guess what? You could use the normal model. Let's verify that we can. Remember, to use the normal model, we need n times p times 1 minus p to be at least 10. So 60 times 0.42 times 1 minus 0.42 is 14.6, which is at least 10. Not shocking, that requirement for normality has been satisfied because we can see from our simulation that the results are pretty much bell-shaped. The normal model is a model that is supposed to describe what would happen if we did do this study over and over and over again. The computer can pretend to do this study over and over and over again. And so it makes sense that the normal model and the simulation match up. And oh, by the way, we need our sample size to be no more than 5% of our population size for the independence requirement. We built our population with 10 million people, 10 million balls, so for sure 60 is no more than 5% of 10 million. And we have our randomness requirement satisfied. We randomly selected the 60 balls, just like we would randomly select the 60 voters. So the normal model can be used, and so we're going to use that normal model to determine the probability of getting 22 or fewer Republicans from a population whose proportion is 0.42. So the population proportion is assumed to be 0.42. We got a sample proportion of 0.367, so I need to find that area right there using in the normal model. In other words, I'm going to go to Stat, Calculators, Normal. The mean is 0.42. The standard deviation was 0.0637. 7? Yep. And we want to know the probability of getting a sample proportion of 0.367 or less. Click compute, and what do we get? We get 0.2027-ish, which is close to what we got from the simulation. The results aren't going to match up exactly just because of the fact that here we're using a normal curve to approximate the proportion of observations that are less than or equal to 0.367. And so we're using a continuous distribution to model a qualitative variable. And so it makes sense that these aren't necessarily going to jive, but the bottom line is there's my p-value according to the normal model of 0.2027. I think another thing to emphasize is here we got a p-value of 0.2542. Up here we got a different p-value of 0.2459. The p-values differ because we had different simulations, different individuals in each of those 5,000 studies. And so when I do a study, I might get a different p-value than you do because of the fact that I have different individuals in my study than you have in your study. And so there's no such thing as, it's not called the p-value for the hypothesis test. It really should be called the p-value based on the data that I collected for the hypothesis test. And so when you do hypothesis testing using the p-value approach, if the probability of getting a sample statistic as extreme or more extreme than the one obtained is small, under the assumption the null hypothesis is true, we do a rejection of the null hypothesis. So when the p-value is low, you reject the null hypothesis. And if you think about this, it should make sense. If the p-value is low, it means the results that you observed are unlikely to occur if the statement in the null is true. Let's see an instance of that. Suppose instead of looking at only 60 registered Republicans, we decided to look at 600 registered Republicans. But we kept the rate of Republicans the same. So we have 220 that said, yeah, I'm a registered Republican. Here, what's the sample proportion that indicated the Republican? Well, p hat is going to be 220 out of 600, which is how much? Yeah, it's 0.367. So I had the same rate of Republicans this go around as I had the previous one when I had 22 out of 60. What's the p-value for this hypothesis test? We'll do it both ways. We'll simulate and we'll do the normal curve. So I'll put that to the side. If we simulate, I got to go to options in my model here, edit, and now instead of drawing 60 balls, how many am I going to draw? 600 for the 600 registered voters. But I still want to know if the proportion is less than or equal to 0.367 because that's the observed sample proportion. Or I could click number and make it less than or equal to 220. Click compute. I'll go out and survey 600 people a bunch of different times. Let's make it 5,000. Boy, that was easy. And what did I get for the proportion that were less than or equal to 0.367? How many times did I observe a sample proportion of 0.367 or less? Only 18 out of 5,000. So is observing a sample proportion of 0.367 or less unusual if the population proportion is 0.42? Heck yeah, it's unusual. So if you observed this result, what would you want to say about the district? Would you say it has the same rate of Republicans as it did before or something else? It's probably less because you observed results that are way less than you would expect to observe if the population proportion was 0.42. So that's one way to go about doing this. A second way to go about doing this is to use the normal model. We will be able to use the normal model because if we were able to use the normal model for a sample of size 60, we certainly can for a sample of size 600, and 600 is still way less than 5% of our 10 million. The only thing that's different is my standard error is going to be different, right? If I use the normal model, the mean of my distribution of p hat is still going to be 0.42, but my standard deviation of p hat is now going to be p times 1 minus p over n is now 600. So 0.42 times 0.858 divided by 600. Now I'm getting a standard deviation of p hat of 0.02, well, 01. We'll just say 020. Now if you think about it, 0.367 is pretty far from 0.42. And when I say 0.367 is far from 0.42, I mean in terms of the number of standard errors. One standard error away would be 0.40. Two standard errors away would be 0.38. Right? So that's about 2.5 standard errors away from what I would expect if the statement in the null is true. When something's more than 2 standard deviations away, you typically say, ooh, that's weird. And so our p-value should reflect the fact that that's weird. And it does. According to our simulation, we should only observe the types of results we observed about 4 times out of 1,000. 0.0036 is about 4 out of 1,000. The normal model says what? I got to change this to 0.020. Click compute. And now look what I got. What did I get for the area to the left of 0.367? 0.004. Pretty close to what I got when I did the simulation. That 0.004 is referred to as the p-value. Here's how I want you to interpret the p-value. We would observe a sample proportion of 0.367 or less if the population proportion is 0.42. In other words, if the statement in the null is true, in about 4 of every 1,000 repetitions of this study. The sample proportion we observed is unusual if the statement in the null hypothesis is true. Therefore, we reject the statement in the null hypothesis. I think another interesting thing to note is that when our sample size went up, the results between our simulation and our normal curve got closer, because as your sample size goes up, it's better, it's more, the normal model is a better fit than it is when your sample sizes are smaller. And if you're going to reject the statement in the null hypothesis, now you can make a conclusion about the overall results. There is sufficient evidence to conclude the proportion of registered voters who are Republican in this district has decreased from 0.42. In other words, it's some value less than 0.42. We don't know what the value is, we just know it went down. So if you were the Democrats in control, mission accomplished. You're probably saying, wow, that was a lot of work to go through to get a p-value. I wonder if my buddy can give it to me directly. Here's how you do this using StatCrunch directly. You're going to go to Stat, Proportion Stats, one sample, and here we happen to have we have summary statistics, the number out of however many, right? So for the 60 sample one, we had 22 successes finding a Republican, because that's what we're looking for, out of 60 trials. Before we checked the confidence interval radio button, now you get to use the hypothesis test radio button. You change the value in the null to p equals 0.42, and you change your alternative to a less than. Notice that StatCrunch uses h sub a, we use h sub 1. Same difference. Okay, it's just notation. And then you click compute, and bada bing, there's your p-value of 0.2013, which is what we got when we did it using the normal curve. If you had a sample of size 600, stat, proportion stats, one sample with summary, 220 Republicans out of 600 is what we got. The proportion stated in the null was that p is 0.42. We have a less than alternative. Click compute, and bada bing, you're getting a p-value of 0.0041, which is exactly what we got when we did this the long way using the normal curve. They differ slightly because of rounding. I rounded my standard error to 0.020, and it was really 0.020149, blah, 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 blah. Right? So again, what we did is stat, proportion stats, one sample, and we happen to have summarized results, so with summary. The p-value is low, so the null must go, is the way we're going to say that. If the p is low, the null must go. Understand that the p-value, yes, it's an area under the normal curve, but more importantly than that, and this is why the simulation is so powerful, it's a representation of the likelihood of getting results as extreme or more extreme than you would get if the null hypothesis were true. Super duper important. Remember the earn. 4.2 million Republicans, 5.8 million non-Republicans, and we sampled from it over and over and over again. How often did we get a sample proportion of 0.367 or less? About 4 times out of 1,000. That is what a p-value measures, and what's awesome about the p-value is no matter what type of hypothesis test you're using, the interpretation of the p-value is the same. So if you're doing an analysis of variance using the Latin squares model, and you have no idea what that means, but it does exist, and you got a low p-value, you would say what? Reject the null. Have no idea how you got that p-value, but I know you're going to reject the null, because if the p is low, the null must go. That's awesome.
Is there a parameter for the p-value to be considered low, normal, or high?
Ah, awesome question. Is there a range of values for which the p-value is low? Typically, we use p-values, the cutoff of 0.05. Right? So if the p is less than 0.05, we typically reject. And if the p-value is greater than 0.05, we typically do not reject. When you read journal articles, what they will typically do is report a p-value to you, and then they put little asterisks next to it. And it'll say things like significant at 0.10 level of significance. Remember that phrase from the last section? the likelihood of rejecting the null when the null is true, right? So they typically say significant at 0.1 level of significance, 2 asterisk, significant at 0.05 or 0.05 level of significance, right? Or 3, significant at 0.01. The smaller the p-value is, the stronger the evidence against the statement in the null, right? And so if you want to be able to reject the null, you're looking for a teeny tiny p-value. So you say, if the p is less than 0.01, we say strong evidence against the null. For p-values between 0.01 and 0.05, you say evidence against the null, and maybe for 0.05 to 0.1, they might say moderate evidence, right? Typically, so that we all get the same answer in a book setting, in a classroom setting, we compare the p-value to the level of significance. And if the p-value is less than the level of significance, we reject. If it's not, we don't. Remember, level of significance is the likelihood of making a type 1 error. That's alpha. Right? So if the p-value is less than alpha, reject. Otherwise, do not reject. And please never say accept the null. You cannot accept the null unless you have access to population data, which we typically don't. If I did this hypothesis test up here where we were using 60 and I did a hypothesis test of 0.41, I bet we wouldn't reject the null either. How could you say I accept the null as 0.42 and then secondly say I accept the null as 0.41? Those are different values. They both can't be true. And so you can't say the statement in the null is true. You can only say the results that I got are consistent with the statement in the null.